Hi, everyone. I'm Carianne Muse. I am the CDC account executive for RTI. I'm pleased to be the moderator of this session today. Very excited to share all of this information. Data modernization is becoming a popular topic within the federal government. For public health, we know that there is a demand for us to invest in new data strategies. There's also a promise of faster, better, cleaner data that comes with the dedication of resources to massive data transformations. The question remains, how can innovations that incorporate artificial intelligence and machine learning really improve our day-to-day data operations so that better, faster, cleaner data actually are a tangible outcome? This webinar will share how RTI leveraged AI and machine learning to reduce the time spent in data identification and cleaning so that we can get to insights faster. The tool is called MetaMatchMaker, and we are excited to tell you more about it. I would like to introduce our presenters who serve as Principal Investigator and Project Director for MetaMatchMaker. Grier is a Senior Fellow in Statistics at RTI, and he specializes in multi-center studies harmonization. And Earley is a research statistician in our Biostatistics and Epidemiology division at RTI, and he specializes in commercial software development. So take it away, Grier and Eric.
Thank you very much, Carianne. Is everybody seeing my talk?
Yes, sir.
Okay, thank you. Hi, thank you all for attending. As Carianne said, my name is Grier, and I'm a Senior Fellow at RTI, and I'm Senior Director of Statistical Genetics, but recently began to, about 2.5–3 years ago, really began to move into AI and artificial intelligence to try to use that to begin to leverage our findings and to try to solve some of the pressing problems that we've been having that science generally has. So I'm going to talk about one of our AI tools that, or actually a suite of our tools that we've developed to try to solve or try to address one of the problems that to increase the speed of science. So I'm going to talk about automating finding and harmonization of data with an artificial intelligence tool that we call MetaMatchMaker. Artificial intelligence, machine learning, neural networks have all begun to intrude into our lives in many different ways, from on our phone with checks being automatically read and signatures being read, to self-driving cars, to Siri and all the other voice recognition tools that we have in our pocket. There really are AI and various AI tools becoming an essential part of our lives to try to make our lives easier. This is also beginning to move into healthcare and biodata, with a number of different federal agencies and government organizations really talking about how AI can be used within healthcare or in various aspects of the government work, and is an essential part of data.gov as well. For the past several years, the NIH has had artificial intelligence working groups to talk about how AI can be incorporated into the NIH's work, and has led to a number of initiatives, including the AIM Ahead and a couple of other initiatives. The CDC has also been doing things through various sessions and things like that, and talking about how AI could be incorporated into public health. So I began to think about what could we do and what could I do to really try to incorporate AI into our science. One of the things I began to think about is I typically work with very large data, work with genomic data sets, multi-center studies, things like that, where we involve bringing together huge amounts of data or just diverse data. And one of the frustrations is that the time for data integration, data harmonization, data cleaning is a large portion of our budget and a large portion of our time. A Kaggle survey said 35 to 50% of the time and budget of a study is spent on cleaning and data identification. Other references say 75%. I would not disagree with at least 50% of the time is on data science. What could we do to try to improve this? Because I think this time is really slowing down our ability to make discoveries. There's a budget just spent on cleaning the data is not leading to discoveries, not leading to greater insights. So what I think is we are fundamentally challenged in the way we do data science. We spend a huge amount of time before we can get to any insights. Let me illustrate this through one of the large studies I work on. This is ECHO, which is the environmental influences on children's health outcomes. This is a very large study, data from 300 sites. Some of the cohorts have been around for over 20 years, something like 20,000 clinical variables. Across all the sites, 100 million years, not 100 million years, $100 million annual budget. But to get to a first release data took 4.5 years. This was frustrating time, a lot of time of working to bring the data together, work out data use agreements, things like that, but it took 4.5 years to get to an analyzable data set. Now, admittedly, a year and some later, 100 papers a year are coming out, but 4.5 years, there were very few papers that came out from this data set because it took so much time to integrate the data and make it usable. So my goal was to try to address this problem, how to use AI to make finding and linking data easier, quicker, and cheaper. I applied to the National Science Foundation to get a grant under their Convergence Accelerator program, which is a mixture of both developing fragile concepts of AI tools, as well as learning about how to develop and user-centric tools. So what I did is I pulled a team together with myself as the PI at RTI, collaborators at Emory and the VA and a for-profit company, Infinia ML, people from Columbia and RTI to try to address this problem, from learning about how to develop software, how to implement AI, things like that. With the ultimate goal of going from the traditional approach where data integration takes, say, 50% of the time of study to one where the data integration takes quite a bit less of the time, so that you have a greater savings in time and greater savings in money, or for that matter, for the same amount of money, you can get greater insights in the same amount of time, gather more insights. We decided to take a transfer learning approach to building our models. Transfer learning typically differs from traditional machine learning, where if you build the model and you test it, it works well in that, but if you begin to move into other systems, it does not work as well. But in the transfer learning, you build your model, you test it, and you can transfer it to other systems with only lesser training data, so that it becomes easier to build and grow your model and apply it in additional domains. One of the things that we wanted to do with this approach was to take the knowledge or the metadata of studies and really begin to try to connect them meaningfully. We did that by turning them into words and vectors and sentences, and then ultimately concepts, in order to begin to bring together the concepts in the multidimensional space, so the things that are similar are brought together. For example, this is an example from a translation, but essentially the concept is the same, that cities are together, animals are together, months are together, but they're separate from other concepts. And that's similar to what we are doing with our approach of trying to bring together the concepts that mean the same and separate the concepts that are different, so that we ultimately get to a multi-dimensional space where the different concepts, or the metadata concepts, that mean the same thing are close together, and those that have different meanings are pulled apart. We began to build this by using a large training data set we had. We being RTI had manually curated a large number of data linking dbGaP to Phoenix. Phoenix is an NIH-supported project developing common data elements to describe that they really are protocols that allow people to collect data in a very systematic way, to allow for there to be commonality of protocol, commonality of data collection across protocols. And dbGaP is the database of genomic data. But it also, in addition to the genomic data, it has a fair bit of phenotypic data in it. And so what had been done was there was a manual training of all the linking from the dbGaP to Phoenix of about 17,000 good terms and a number of negative terms. We began to build models to test this by using some training, some validation and testing paradigms to begin to evaluate different systems or different machine learning approaches to linking the metadata concepts. Had to do a little bit of processing to clean up the data, some vectorization, bringing together the data together, and began to evaluate a number of different classifiers. These are just different kind of core learning, machine learning tools that we used, including some transformers like BERT and DistilBERT, hybrid models, just regular neural networks, attention models, and swim models. And what we found was that there's a surprising difference in the performance of the different machine learning models. These are just different measures of the accuracy of the model that we built in the training data set and we validated later. And what we really did settle on was a hybrid model to use for building our model because of the consistent performance across a number of different situations. So we used that core neural network to build what we call our core neural network, which is the MetaMatchMaker neural network. We built it initially upon the dbGaP to Phoenix model, but began to incorporate additional data, additional training data from BioLink and FitBERT to begin to build the core neural network. Initially, when I had conceived of the concept of MetaMatchmaker, the goal was really just to make it easier to find data. But along the way, I recognized that the process of finding data, which is just finding variables within data sets, and linking data, or rather the metadata, really are the same concept. They're just, and the same core neural network could be used in two different ways. And we used it to develop two different tools that I'll talk about. The first is M3Find, which is a tool for finding data, and M3Link, which is a tool for linking metadata between studies. So let me first talk about M3Find, finding data easier. And I'm going to try to run a video demonstration of the tool that takes about 2.5 minutes, and hopefully the technology works for this.
Universal interface where you can search and find data to harness the power and potential of data already collected to answer a research question. Let me show you it in action. Let's say I am a researcher interested in finding data to understand links between fetal outcomes and smoking during pregnancy. I might first type in the search term pregnancy. By hitting Tab, I'm allowed to enter other search criteria, such as smoking. By searching pregnancy and smoking, I will see a resulting table with all of the studies that match those search terms. I will see the study, the sample size of the study, how many variables within the study match, the study type, the source database of the study, a link to learn more about publications associated with the study. If I select the entry, I'm able to see information about the matched variable to my search terms. So in this example, we see that the GATE study has one matched variable called smoking during pregnancy with 531 data points submitted against it. If we wanted to change our criteria from and to or, we would expand our search criteria and see more studies. Here, you can see that the Framingham cohort has 88 matched variables. The interface allows you to search through and investigate the linked variables for each of the studies in the results. You could also use the NOT operator by searching pregnancy, not smoking, to eliminate variables associated with smoking. Here, you can see the studies that are returned as a result of this search. If you're interested in more information about the study, you can select the study title, and a new tab will open showing you information about the study from the source database. Additionally, you can select PubMed to see associated publications in the pubmed.gov repository. The table results in its entirety can be downloaded by selecting this option here. Additionally, the table can be filtered using these easy-to-use toggles. For example, updating the minimum sample size and selecting the database of interest.
So that is an example of the M3Find tool initially trained upon for databases, but what we would like to do is to grow it, and it has the ability to grow to be able to link many more data sets to make it much easier to find data. Because one of the big issues that we have in biomedical data and health data is there are so many different data repositories. Once I started looking, I think there's at least 40 or 50 different data sets that could be, or databases that could be linked, but really probably are more than 50 if they're not 100 or 200 databases. And really finding the data is a real problem that often you have to look into different studies and get into data access and like that. So one of the goals of M3 Find is to grow it, to make it much easier to find data so that you can begin to plan and initiate your studies much more quickly. One of the aspects of the Convergence Accelerator program is we did a lot of interviews with users or potential users of our tool. And really our users drove what we need and what we developed. And along the way, one of the things that we realized, or what the data stewards said, is they wish they had a magic button to just automatically integrate data for me. And what we decided to do was to take our core neural network, M3, and begin to develop another tool called M3 Link in order to make it easier to link data. Right now, we are really just focusing upon metadata harmonization. We're not going down the further steps of harmonization, including the ELT coding or the dealing with study-to-study variability. But right now, we're just focused upon metadata harmonization between data sets. What the goal of M3 Link is to be able to take data across multiple studies where there are many different variables within each study, and then pull them together so that you can begin to bring them together more quickly and more efficiently by pulling together things that mean about the same thing. So we've developed a tool called MetaMatch. We've developed a tool into M3 Link, which is also available. It's actually at this kind of unpleasant website right now, but what it allows us to do is to be able to link data sets, and I'll talk about that a little bit more in a moment. But I'm going to give you also do a live demo of the M3 Link. This is one just using toy data sets of each about 100 variables of a target and a source, where our goal is to try to bring together two different data sets. And you're able to just take one data set and another data set, and the core neural network then begins to combine the data and identify what are the best potential linkages between them. You have the ability to set how good of a score you do. You can see we give a score for the link. This is kind of the output that comes out of, in one data set, you have children's weight. Within the other data set, there's a couple of different variables that seem to link: weight of subject, patient's weight. All those variables seem to be linking together, FVC, and there's no other terms that link there. Then weight associated with spirometry. So that what you saw was that M3 Link was able to bring together these two relatively small data sets relatively quickly, but we also have been able to, we'll talk about a much larger data set that this runs very quickly and provides the best options for, based on the neural network model, for what are the variables that link between data sets to make it easier to bring the data sets together. And if the data is structured correctly, it should be able to work on any data set any data sets and bring them together. And then just identifies the best link. Now, one of the things we also wanted to do was to begin to prove the utility of MetaMatchMaker, both M3 Find and M3 Link, as also through our user experience, we began to realize that a lot of people are selling AI solutions, that we need to begin to move from promise to delivery. So what we've begun doing is really trying to build out some use cases to both establish the utility of the tool, but also to establish the cost and time savings as well. So we're currently working on 3 different use cases. One is, and I'll talk about this more, about merging a couple data sets together to go to a common database, and we'll talk about that for the latter. Then I'll talk about linking multiple databases together to one another, which is going to be a dbGaP to Phoenix mapping. And then I'm not going to talk about this, but merging multiple databases onto a single database, such as submission of data to a data repository, as well as merging multiple data sets into a single data. But I'll talk about a little bit about the first 2. So the first example is kind of the latter, or the linking Angelman and duplicate 15q data for expanded research. This is funded by the Angelman syndrome, and the goal is to bring together a couple of databases in order to make pull the data together so that both joint analysis can be done, meta-analysis, but also to just encourage other people to use the data. One of the things that was very interesting as we began to dive into the use cases was we began to realize that not everybody agrees with what is a match. And as it's evolved, and what I mean by that is we have found that there's different opinions on what is a match. Some people want it to be exact. Some people don't want it to be exact. Like, for example, does chronic lymphocytic leukemia map to chronic lymphocytic leukemia only? Should it also map to leukemia? Should it map to cancer? Since they're all meaning, but there's some mother-daughter relationships. Things like, does BMI as a quantitative measure link to obesity, which is a discrete measure, or BMI greater than 30? There are various opinions about what is mapping. So as we begin to get into use cases, we began to realize that we really have to have a dialogue with people about what they mean by mapping. And so that, yes, we've got a core neural network, but there needs to be a little bit of tuning of the model for people as they begin to get into the model to make it map for what they want to do. And so what we begin to do is develop a series of questions with people to understand what do they want to match, what don't they want to match. How important is, did you have a disease versus do you have it? Do you consider gender and sex to be the same, different? All those things can impact your matching. And so we've developed these kind of questions in order to define the mapping, and then we can incorporate that into a model through training data, and are able to take our core neural network, train it, and begin to build the data, sometimes with an iterative process to improve the model. But what we can do is tune the core M3 neural network to anybody's particular situation about matching, and what type of matching they like to do, what type of matching they wouldn't like to have. So what we've been able to do with the latter is essentially go through, run it, and been able to show that we can get good matches for them. And this is a data set that's actually, they're working with us because this is one that can be mapped manually because it's only a few hundred variables from group to group, but a tougher mapping, and one that we are actually doing a much more systematic and deep evaluation, is really of dbGaP to Phoenix mapping. Remember, my initial training data was on dbGaP to Phoenix mapping, but it was all data submitted before a set date. There's interest in mapping all the Phoenix to dbGaP tools with more recent data. Like, as I said, Phoenix is now a larger data set than was originally trained. Now it has 900 measures and 9,000 items. There's unfortunately some redundancy in the measurement, which did cause some issues. And that there have been over 70,000 non-genetic terms submitted to dbGaP since June 1st, 2016. So I'm not attempting to do any mapping of SNPs or genes or anything like that with dbGaP. These are just the phenotypic variables within Phoenix. So what we were able to do is to take our M3 find tool, or M3 link tool, to be able to combine the Phoenix and dbGaP tools. We did some filtering, found initially over 6 million matches because there's a lot of possibilities with a good score. We began to start filtering it down and began to look at how accurate are we getting on our scores. Our scores we get for accurate, when we begin to link terms, we go from 0 to 100, 0 to 1 in our mapping. We're able to run this very quickly. We looked at the 32,167 matches that had a score greater than 0.99. The manual review revealed that about 79% were true positives. Unfortunately, still 21% were negatives, but there was we were markedly able to identify the true variables links between dbGaP to Phoenix. And we are beginning to improve the negatives to improve the model to begin to go down further down the list. And we are estimating that at least a 50% reduction in effort from use of this tool to make it more easy to link data concepts, especially across something as deep as this, where you're trying to map 9,000 variables onto 70,000 variables, which really is extraordinarily difficult to do manually. Admittedly, and this is admittedly, there's a many-to-many mapping between these databases right now. So in summary, what we've done is we've taken AI tools in order to approach data science to make it easier both to find data through M3 Find, as well as to link data with M3 Link, with the goal of making faster data integration that can lead to savings in time and savings in money, or better yet, to yield greater insights in a more rapid manner. Thank you very much, and I'm happy to answer any questions.
Great, so I think we will start some question and answers. There's been a little bit of discussion in the chat, and I'd love for us to, even though some of them were responded to in comments, to maybe expand on those. And so we'll go through some of them. First of all, the housekeeping item that was asked about whether we'll have access to the recording. The answer is yes, you will be able to access this presentation after the fact. So we'll make sure you get all the links that you need for that. The first question on the data and the tool itself is about if the tool can be used with clear assurances that PII will not be leaked. And Eric addressed that in the comments. I don't know if Eric, you wanted to expand on your response or have Grier also answer.
Sure, yeah, I actually realized when I typed it in, it only went to the panelists. So I don't know if people saw it. But yeah, what the demo that Grier showed was actually not even on data themselves, it was on the study variables. So for example, if you're doing a study on, let's say, heart attack, it would be the column that says myocardial infarction or heart attack or whatever. So it's not really considered PII in that case.
It ultimately in the future, additional tools could, we hope with AI, could get down to the actual mapping of the data and say the recoding of variables and things like that. But right now, this tool is just focused on kind of the very top end of data harmonization, which is the metadata and the variable harmonization, which is really just the data discovery and the metadata concept harmonization, which is really the first step in harmonization. And as we build these better, then we can begin walking down the harmonization process. But right now, there is no PII data within this. Everything we've done has been off of data dictionaries and off of just the variable headings from the databases.
Great, and can you speak to maybe, Eric, this is more future looking, I think, than maybe you'll be ready for. I apologize for putting you on the spot, but thinking through what we just talked about, potentially putting PII data in later, what are the plans for securing that data so that it wouldn't be something that would leak out, as was stated in the question?
Yeah, we would, if we were to do that, we could not do the tools right now, which are just web-based tools that are relatively front and center. We would probably have to build it into a much secure infrastructure without, admittedly, is quite as easy of access and things like that. We have a number of studies that require at RTI that require FISM moderate solutions. Echo is one of them, and many other ones are like that. So we would have to set up a much better security infrastructure once we get to actually using PII. So that is something that we are aware of, and we haven't. It would be nice also to be able to verify people, like could we integrate with login.gov or one of the GA4GH's passports for data access, so there'd be a lot more control over who would be able to upload data to. So we have been thinking about data access and data security as well. But we're not yet at handling PHI or PII data.
And just to expand on that, the demo that Grier showed off you'll notice has that gnarly web address, it's an IP address. And that kind of shows off that what the state of things is that we're creating what we think is a really reliable core model neural network and a code base that we can deploy quickly in different situations like you're describing in maybe a HIPAA compliant cloud infrastructure. We have the code base for M3 is on GitHub, and we're actually just about finished up with revising the code base, so it is very easy to deploy, for example, using a Docker image or something like that in a workflow that if you wanted to. But the demo we put together here is just kind of a rough way to show off a use case. So we are really excited to learn about new, interesting ways this could be used to enhance your work. Because we've done a lot of user interviews, and the idea for the M3 link tool actually came from users saying, data findability is great, but linking it would be really cool.
Okay, thank you. That sort of leads into the next question from Carla that says, will this be expanded to include databases that include geographic data to link to or link with structural or social determinants of health databases?
Ultimately, yes. It should be expandable. Like, it depends on budgets and things like that. We've got initial money from the NSF, and then we've got a little bit of pilot money from RTI that we're building and growing. There really is no particular limit to how much it can grow, and we hope to grow it. It's one of the things we'd like to do is be able to work with people to really begin to bring in additional data and additional data sets. Because one of the things we're finding is that every time we add a new data set, we begin to find new data, and we have to retrain it. Like, we started pulling in a sleep data set, and Phoenix and dbGaP have relatively little sleep data, so we actually got a whole number of new variables we had to train. So really, as we go out, progressively go from the core data of Phoenix and dbGaP and BioLink, which is NHLBI work, and FitBER, which is PTSD and neurotrauma. Each time we go out, we have to do a little bit more training, so it takes a little bit of time to add new variables because there's definite concepts that have to be mapped in. But I'm sure there are limits on what can be incorporated, but it's a matter of time and having the training data that can be used to grow it.
And thank you. So then also there's a question from Timothy Slade. Actually, there are two questions. I'm going to read the second part of it first, which is about databases that are currently indexed by M3. Which databases they are?
It's just the FitBER, BioLink, and dbGaP, as well as the common. I didn't show the demo didn't have the common data elements, but there's the common data elements that come out of Phoenix, which I call them common data elements. They say they really are analytical tools, but I call them common data elements for shorthand. But they really are just data elements. So it really is just those three databases plus that underlying variables in Phoenix.
Okay, and his second question was, how do I start using M3 on my projects right now?
Well, we have that website actually with the gnarly website works. You could use it now. But one of the things that we would love to do is really talk to you and talk through the examples, because I think that core neural network will work okay, but it really needs to go through the retraining process to make it a little bit better. And that what we think is that the core neural network probably for each project will have a little bit different training, and it'll work better for each situation. So one of the things we'd love to do is to work with people to take the core neural network and train it to work in y'all's systems better to fit your data, because the model is based upon what it's been trained on, which is admittedly a little bit limited, but we have the ability to retrain the model very quickly within a few days once we have the training data.
And then Karen Kessler refers to the ECHO project and is wondering when we might get some of this embedded in that project. And then also, do you need to identify the terms that will be linked? Both questions from Karen.
Essentially, you essentially take, right now it's set up to do multiple lists of data. So essentially you just have to be able to extract the variables. Usually you want the full name of the variable, not just the abbreviated list, so that the machine learning can recognize the context of the words. And then there's a relatively simple structure. I can show you that many, like this is, can you all see an Excel spreadsheet?
Mm-hmm.
This is really just the variables that we put in for the training data, and really just different names of different variables. And that's really the only real input that you need. And then this is the target, and the source looks very similar, that it really just needs to be the descriptions of the variables. And then the tool can work on it right now. And so anything you put in, it will do its best to link. It actually, everything you put in will be linked. Everything, it's just a matter of the score. I had shown that you can actually kick out everything that matches, because one of the pluses and minuses of these type of tools is if you put in 100 variables and map it onto 100 variables, you get all possible combinations all linked, some with good scores, some with bad scores. So it's very important to filter the scores, but you can get everything that's put in does get linked. It gets linked to everything with a score. Some of them are going to be very bad scores and shouldn't be linked, but then that's why we do the filtering to identify those that are the best links.
We don't have any additional questions in the chat that we could go over right now. I'm not sure if we can take live questions or not, but I actually would like to hear a little bit more about the RTI innovation that we've been working on with CDC related information. What are the next steps, immediate next steps for that? Or are you wrapping it up?
What we're really trying to do right now is at least really try to fulfill these use cases to try to really begin to establish the value of the tool. Like, as I showed, we've been going through and systematically evaluating the linking to prove and establish the validity of the approach. And then also one of the things we're trying to really work on is try to establish what is the cost savings. That's a little bit harder to get to, because it's hard to know how much time people manually spend linking data. Like, we know how much time it takes to generate the training data, but in practice, we're trying to get a good estimate on the actual time savings in order to establish the value of this to the systems. So that's really what we are doing, is really quantifying the accuracy, how much increase in accuracy you can get, and how much savings in time and budget are possible. And those are the ones that we're wrapping up I only talked about 2 use cases, but we've got 3 use cases we're working on.
Yeah,
Oh, I'm sorry, I want to interrupt real quick. For those that are here as attendees, if you would like, you can use the raise your hand function, and I will give you the abilities to take your microphone off mute and ask your question live if you would like to do so. So certainly you can do that. Sorry to interrupt, but Carianne, back to you.
Oh, no worries. Thank you, Cameron. So that's wonderful. I think from my perspective, of course, showing that value proposition to the government from our internal innovation on this is going to be crucial to making sure that we can actually leverage it and change some of the ways that we do business with them and how they get to their insights faster, which is the whole point. So
yeah, because one of the things that we really would like to do is grow the whole model. That's when we had proposed the NSF for kind of continuing funding, was really to grow it to include the different databases to make it a much more usable tool. But yeah, it's really is just, we think it can be it works. We've been working on public repositories, but there's no particular reason why it can't work with electronic health record systems, especially not the PHI data, but just the variable terms, things like, just the variable terms, anything where there's not PHI or PII data where we can extract essentially variables, we can link it in and make the data both linkable as well as findable. And that's actually one of the things that we've had some discussions with EHR systems and some things like where people are monetizing the EHR systems, is how could we make they would love to allow people to access their data through a subscription model or through data requests, but how do they make it known what their data is. If they could integrate it into the M3 find, it could be able to be linkable to be able to monetize through EHR systems and things like that, or other databases that are not fully public. And then EHRs could then work out whatever data use agreements they give to make access to the private data as well.
Yeah, I know that will be exciting. Lots of talk about how we can do a different methodology for surveillance in the future, and it is probably going toward figuring out harmonization with EHRs that are it's already kind of moving in that direction. So thank you. Okay, if I don't see any hands raised, Cameron. I don't know if you do.
I do not at the moment either, no.
Anything else that we would like to add in conclusion here, Grier or Eric?
I would just say that I appreciate you listening. We really would like to, we really are still developing the MetaMatchmaker tool. So we do have a website, I should have mentioned that, MetaMatchMaker.com, that has, it doesn't have, the tools aren't live there, but we have a kind of a contact point there. And that we are continuing to develop this, and we really love to build partnerships with groups to really begin to understand what people's needs are and figure out how this might be applicable to novel and innovative solutions in order to make science happen faster.
Great. And Eric, anything?
No, it's been a pleasure. Thank you all for attending.
All right, thank you, everyone. We appreciate your attendance and we look forward to interacting with you more. Please feel free to reach out to us if you want to get more information or if you have more questions, and we will publish the links for this video so you can share with others. And thank you very much. Have a nice one.
Thank you.